The outline of my talk is the following. First, I will give a general motivation for this work. Then I will present quantum van der Waals model. After this, I will discuss the quarkyonic matter theory. Then I will show how these two are merged and the results of computations, in particular for the speed of sound at high baryon densities, which is relevant for neutron star phenomenology. So, to understand the motivation for this talk, let us address the schematic picture of the phase diagram of QCD matter in terms of temperature versus baryon density. Quantum chromodynamics is not computable everywhere, and here are depicted different pockets of computability. So perturbation theory can be used only at very high densities or temperatures where quarks become asymptotically free. Here, ρ0 is the density in the ground state of nuclear matter. The non-perturbative approach of lattice QCD is limited to low baryon densities by the so-called sign problem. The severity of the sign problem increases at low temperatures. One of the most reliable theories to describe nuclear matter at low temperatures is considered to be chiral effective field theory and its modifications. It is rooted in the symmetries of QCD, but it is an effective theory with effective degrees of freedom, and it is considered reliable only till densities of approximately 1.4 to 2 nuclear saturation densities. Outside of these pockets is a no man's land where the variety of different phenomenological models exist, which try to interpolate between these computable theories of QCD and also to describe and predict the experimental data. One of such models is quantum van der Waals model, which I will discuss later in the talk. In terms of experimental data which probe the QCD phase diagram, there is early universe at low baryon densities. Heavy ion collisions probe high temperature region with intermediate to low net baryon densities. Neutron star exists at almost zero temperature, but high densities of presumably about 2 to 3, maybe larger, nuclear saturation densities in the core. And neutron star research has become increasingly active in the recent years. Finally, there are binary neutron star mergers which probe extreme density region and finite temperatures. For instance, observations from neutron star indicate that with a very high probability, speed of sound inside neutron stars is non-monotonous. The speed of sound increases with density, so matter becomes very stiff, but then at some point there is a drop in the speed of sound, after which there is a slow increase again to reach the conformal limit of 1/3 predicted by perturbative QCD. The sudden change in the equation of state at high densities can be a result of transition to quark matter. Moving to quantum van der Waals model, it is just a simple phenomenological equation of state. Probably it is the simplest model which can describe the nuclear gas phase transition. It is a generalization of classical van der Waals equation of state on grand canonical ensemble and quantum statistics. Like in classical van der Waals model for molecular fluids, the repulsion between hadrons is modeled by excluded volume correction, and attraction is modeled by attractive mean field. Parameters A and B regulate respectively the strength of attraction and repulsion between particles. If A and B approach zero, the expressions reduce to expressions for an ideal quantum gas. We fix the two interaction parameters A and B from the known properties of the nuclear ground state, so there are no free parameters. Despite its simplicity, it is quite successful in describing nuclear matter, nuclear critical point, and critical fluctuations. When extended to include all hadrons and resonances, The model can also describe lattice QCD data on thermodynamic functions and conserved charge fluctuations. Also, it well describes heavy ion collisions data on produced particle multiplicities. The limitations of this model is that it doesn't consist quarks, thus it is not applicable at high densities, can be applied to neutron star matter, and it is not consistent with perturbative QCD. So we attempted to extend it by including quarks in a specific way based on quarkyonic matter theory. Quarkyonic matter is a concept inspired by large NC limit, where NC is a number of QCD colors. In the large NC limit, QCD simplifies, and one can show that at low temperatures, confinement persists till very large densities, where energy of interactions between quarks is already larger than the scale of confining interactions. Quarkyonic matter is some intermediate state between hadronic and quark matter, which is still confined. However, we can describe its constituents and their interactions as being quarks, since most interactions are at very high energy. The assumption is that NC equals 3 is sufficiently large for something like this to happen in our world. To describe this situation phenomenologically, a very simple model was recently proposed and became quite popular. It describes high-density matter at zero temperature as a mixture of nucleons with excluded volume and non-interacting free quarks viewed as quasi-particles. Nucleons consist of 3 quarks. Pauli exclusion principle acts between free quarks and quarks within nucleons. Because the degeneracy of nucleons and quarks is the same, it effectively means that nucleons and quarks Pauli exclude each other. So nucleons and quarks cannot occupy the same momentum level and thus separated in momentum space. Quarks occupy low momentum states while nucleons occupy high momentum states. This is model assumption. At each baryon density, one should minimize energy density to find the quark fraction. One can see on this blue and pink picture how matter evolves as density increases. Note that it is not coordinate space, but a momentum space. One of the reasons this model is popular is because it produces the peak in the speed of sound for neutron stars. However, weaknesses of the given implementation is that it is not consistent with lower density nuclear theory, namely with nuclear liquid gas phase transition, and it contains 2 free unknown parameters, excluded volume and lambda, which regulate respectively density and height of the peak of the speed of sound. So in our approach, we took a quantum van der Waals model for nuclear matter with parameters fitted to the nuclear ground state properties and extended it to higher densities, assuming that when it becomes energetically favorable, a Fermi sea of quarks forms on lower momentum levels, so nucleons are pushed to higher momentum. You can see it on the right plot, which shows momenta of constituent particles as a function of density. At low densities, matter entirely consists of nucleons, and at high densities, almost entirely from quarks. For quantum van der Waals interactions, quarks start to appear at densities which is only slightly higher than nuclear saturation density. We also consider 2 additional modifications of excluded volume factor, namely Carnagan-Starlin and trivial model, which are slightly better in describing incompressibility of nuclear matter in ground state. So this is a result of calculations for energy per nucleon, quark fraction, and speed of sound for different realizations of excluded volume factor. In all cases, speed of sound exhibits peak which overshoots the conformal limit and is located at relatively low density of 1.5 to 2 nuclear saturation densities. Unfortunately, the infrared regulator with lambda parameter still had to be used to limit the peak in the speed of sound. Otherwise, it reaches values which are higher than the speed of light in vacuum. We also considered the recently proposed alternative approach to quarkyonic phase, the so-called baryon quark matter. It is quarkyonic matter, but inside out. It assumes that nucleons occupy the low momentum states and quarks. Quark from EC is located at high momentum. We found that for all considered scenarios, baryon quark matter is more energetically favorable than quarkyonic matter. Also, the onset of quarks in baryon quark matter is more gradual, and thus, as a result, the infrared regulator is not needed to limit the speed of sound. Therefore, the model doesn't contain any free parameters. So let me outline the possible further directions of this research. First of all, the effective quasi-particle approach is just the first step. In reality, if quarkyonic matter exists, it should have dual description, meaning that we should be able to describe quarkyonic matter as having only baryons or only quarks as degrees of freedom. Both descriptions should be valid, however, not necessarily equally convenient, which may depend on density. The first attempt in that direction has already been made. See the preprint by Fujimoto et al. But as for now, no realistic interactions are implemented, and the speed of sound in this dual description is singular. Secondly, even for quasi-particle description, if we introduce some quark-baryon interactions, we can limit the speed of sound in quarkyonic scenario without relying on infrared regulator and lambda parameter. An obvious application is to neutron stars, which is in progress. In this talk, we considered only symmetric matter. In neutron stars, matter is asymmetric, meaning there are much more neutrons than protons, and one should calculate different Fermi surfaces for protons and neutrons. And also other complications, the difference in proton-proton and proton-neutron interaction should be taken into account. Simultaneously, the speed of sound should stay below unity in the whole range of asymmetry parameter. And finally, an extension to finite temperatures will allow to apply the model to binary neutron star mergers. So in summary, we have extended the quantum van der Waals model to include quarkyonic phase at high baryon density. In contrast to previous works, we incorporate the empirical properties of nuclear matter. The model predicts in transition to quarkyonic regime at densities around 1.5 to 2 nuclear saturation density, with speed of sound rising significantly above the conformal limit. Baryon quark matter is more energetically favorable than quarkyonic matter for all considered scenarios and doesn't rely on free parameters. And there is a number of topics that we can study in the future works based on the present study. Well, thank you for attention, and I will be glad to answer any questions.
Thank you very much. We have time for questions.
You are saying that your model is extension of the pre-existing model. What specific changes did you make?
So we allowed quarks to appear. But so we added a new type of particles, quarks, which are not non-interacting, but they appear in a special way. So they can occupy only In the case of quarkyonic matter, only the lowest momentum levels. In the case of baryon quark matter, only the highest momentum levels.
Let me continue this question. In the region 1, 2 normal nuclear density of neutron star, I think that there are hundreds of papers where people calculated all quantities, including speed of sound. And if experimentally it is known, I don't know, then I'm sure that people fitted this maximum of speed of sound and other features. So the question is, what are the differences in your model? Do you have some principal difference or numerical difference or qualitative difference from hundreds of or thousands of previous investigations of neutron star?
Well, we have not applied it to neutron star yet, but we made a first step in that direction. And our model is, it implements the empirical constraints of nuclear matter, and it is also based on that quarkyonic concept, which is very popular now.
So at the moment, we have no data to check your model. Is it clear?
No, we have data. We have some data.
What type of data?
Empirical estimates.
We have no data, only inside neutron stars. No other data.
Yes. So from neutron stars.
You claim this is not for neutron stars. This is for symmetric matter. I don't know.
Yes.
Yeah, but then there are no data. So at the moment, this is some prediction.
But no, we did some calculations for asymmetric data with this model, and it produces peak in the speed of sound at densities which are lower than empirically estimated to be the most probable from neutron stars.
Okay, thank you. Are there any questions?
Sorry, what it means quark-baryon interaction? It's clear quark interacts with clear baryon. What it means?
We try to introduce
definition of this interaction.
The screening of repulsive interactions between baryons by quarks. So some type like Thomas Fermi screening. Mm-hmm. When the density of quarks increases, the excluded volume decrease because they like screening repulsive interactions. But this is work in progress.
Mm-hmm. Thanks. Thank you very much.
Thank you very much for this talk.